All right, it's a full house, so we're going to get started. Hopefully you guys can see the bottom of the screen over here. If there's something important there, I'll just slide the TV around. So hopefully that doesn't obscure any of the front row seats. So we're going to build Nintendo games today, like real ones, which is going to be super cool. I have, if you're wondering, like, how the heck do you deploy Nintendo code? The answer is which one of these? You can buy a Power Pack retro card, which allows you to stick compact flash into it and load up your own ROMs. So that's how you do it. So if you're like, how would I print a card? You know, like the answer is you find a hacker online that likes to do this stuff. It's a little pricey. All right, so anyway, we're gonna build Nintendo games. My name is Eric Onerheim. For you guys who don't know me, I see some new faces in the room. My blog is up there. It actually does get updated now. It's not just a thing that I have there. I have a blog post about this very Nintendo and how there was like a gallon of Surge spilled inside of it. And I repaired the Nintendo. So if you want to see how to repair a Nintendo, check out my blog. Also, you can tweet at me at Eric Onerheim. That'd be cool too. Or follow me. You know, I tweet almost nothing. So I only retweet. I'm only a lurker. So all right, let's get into it. So a bit about me. If you guys have seen me around, I'm a DevOps engineer on the web hosting team. I'm the loud one in Fuse, so if you haven't seen me, you've definitely heard me, because I laugh really loud and I complain really loud. I'm also a software developer. I make games in my spare time. I'm a video game enthusiast. I own a lot of video games that I have not played. I guess I'd be a collector that doesn't play. It'd be like a car collector that doesn't drive cars. That's me with video games, like, or comic books. Like I have a shelf of comic books, like half of them I haven't read, you know. I also maintain an open source game development library with a couple of the goons in the audience here, like Kamran and Alan, and my roommate who is not in the audience. But if you want to check it out and make a video game for HTML5 stuff, you can check it out and tell me how bad it is, and then we'll fix it. Cool. All right, let's talk about the Nintendo. The Nintendo Entertainment System is probably one of the most prolific consoles, and if you heard me this morning, there is only one Nintendo. There's not more. There's only one. It's one of the most prolific consoles in history. It single-handedly revived the video gaming industry after the crash in 1983. It was built really sturdy. This guy can survive a can of Surge being poured into it, and you can revive it. It's pretty impressive. The only, say what you want about Nintendo, but I fished a Game Boy out of a lake that was running, and it still works. So, I mean, maybe the Switch, they took a step down a little bit, but it's pretty impressive. Like they battle tested this. There was a Game Boy in a museum that was bombed in Vietnam. That still works. It's like all melted and gross, and it works. It was amazing. So, all right, so, brief history of the Nintendo. It was released in 1985 in the US. It was released earlier in Japan, I think 1983. In 1983, there's this huge bubble in video games because there's a lot of crapware that was coming out. It's like grab for money. So a whole bunch of people wound up not trusting the video game industry. Like there were a lot of Atari games, like especially I think E.T. is cited as the reason why the video game industry collapsed because people are like, oh, we spent $60 on this game. What? So that's where the official Nintendo seal of quality came in, and it's traditionally and still is incredibly difficult to get your game licensed by Nintendo because if they don't like it at all, you won't get on their platform. So that's kind of how they keep Nintendo like a really solid platform is they rule it with an iron fist. It's a little easier now on the Switch, but not by much. You still have to sign an NDA and they own your soul and firstborn and all that stuff. Standard operating agreement for game developer. So a little bit about the hardware. The Nintendo itself runs an 8-bit processor. It's an 8-bit machine. You know how people will say, oh, it's an 8-bit game. That's not necessarily true in like modern sense. When you see a retro game and they're like, oh, it's 8-bit. It's like, no, that's not. This is actually 8-bit. It's an 8-bit processor, 6502, which is running at 1.79 megahertz. So it's slower than your Pentium. But it also has a 16-bit memory address bus, which means there's 65K of RAM for you to use. That's actually a lie. You have much less when you're writing a game because a lot of that is used by the Nintendo to do Nintendo things. They have a custom-built picture processing unit, which is a graphics coprocessor. It is the graphics card of the Nintendo, if you can call it that. It is capable of rendering 48 colors that aren't black. There are 6 blacks that you can render. I don't know why they decided to put that many in the palette. Like, I feel like you could have just done like 1. But the thing is, I think a lot of game developers use it for copy protection. So like they could sense if like the color wasn't right or something, like if someone copied their game, like they have all this tricky code to like sense the color that was being displayed. Yeah, so I don't know why they did that. But there's 48 beautiful colors. You know, you can use them to make Mega Man, which they really exercise the palette quite a bit in that one. The display is 256 pixels wide by 240 tall. There's a custom APU, which is the auto processing unit, which I'm not going to get into too much today other than to tell you that it's there. I'm not an audio engineer, and in order to do it, like you gotta send bytes at it to make sounds, and I just couldn't figure it out with the time I had. And then there's the infamous 10 NES lockout chip, which is responsible for most of the red blinking of death on Nintendos. And I go into it in depth in my blog. You can look at it there. But so the processor itself is a 40-pin DIP. So here's a picture of the processor itself. It's got 40 pins. It was a popular cheap processor, and actually Nintendo has a history of going for the popular cheap processors out there. The Game Boy ran a Z80 processor, which is pretty much in everything. The 68502 was in the Commodore 64, the Atari 2600, the Apple II, the Tamagotchi, and the most famous thing to run a 6502 was the Terminator. In the movie, he has a readout on his screen, and he's running 6502 assembler code on his HUD. So, you know, get to Nintendo, you know. So, you know, this is some high-power stuff we're talking about from the future. Okay, so here's a picture of the Nintendo board itself. This is actually that board in there, because it's my Nintendo. And you can see over here, there's the 6502 processor. They had a custom build because they have some memory map stuff, but it is a 6502. Slightly different, but it's mostly the same. There's the PPU, and then there's the infamous lockout chip, which you can disable. You can't see it right here, but under the capacitor right here, this little blue thing, pin 4 right there, if you snip that sucker, lockout chip don't work. So you can play any game you want, pirated games, bootleg games, anything is, the world is your oyster. If you're okay snipping part of your PCB board. I didn't go for that, but you know, you could do it if you want. Anyway, so we're gonna get into assembler, and the unfortunate fact of life in assembler is math is done with hexadecimal. So how many of you know hexadecimal? All right, cool. We're gonna do like a quick primer just to make sure that we're on the same page. But basically, you know, in our convenient base 10 system, we have 10 digits for counting. In binary, we have 2 digits for counting, and hexadecimal we have 16, which presents a problem for the normal human because there's an extra 6 off the end of that 10. So in base 10, when you get to the number 9, you roll around to the next digit. In binary, when you get to 1, you roll around to the next digit. And hexadecimal, when you get to 15, you roll around to the next digit. So, over here, things are tracking pretty well, I think. 0 is 0 is 0, 1, 1, 1. 2, like binary is like, okay, I get it. It's the power of 2. That's the 2's place. So I have 1, 1, 2. So that's a 2, So far, so good. Things get a little sketch when you get to 10. It's like, A, there's letters in my math. I didn't think this was algebra. 10, we wrapped around in base 10. We got to 9, and then we went over to the tens place to indicate we have 110. In binary, we have 1, 2, and 1, 8, and 1, 2 plus 1, 8 is 10. In hexadecimal, we have A. So it just goes A, B, C, D, E, F. And after a while, it's kind of gross, but you start to recognize patterns. Like, I just see C as 12 now. It's super weird. Like, and I had a dream last night about hexadecimal. That's when you know you've crossed into a weird territory. And it's just like, I'm like, if I load hexadecimal, oh man. So it's pretty crazy. So this is what it looks like. We'll get into the specifics here a little bit, but man, that is some low contrast screen. I wish I could make it better. That is an image, unfortunately. But this is a 6502 assembler, specifically a Nintendo-based assembler that someone wrote on the internet. That's kind of gross. You can't assemble from other directories or anything. It's a pretty gnarly assembler, but it works. You'll notice that there's opcodes over here on the left. There's numbers that look like hexadecimal, which they are. And there's all sorts of different stuff happening in 6502 here. And we'll get into those bits here in a second. Man, if I had known it was going to be this low contrast, I would have done something different. So let's talk about numbers. So I told you that the 6502 has a 16-bit address bus. They also, in 6502, you can do what's called zero-page addressing. And that's when you omit 1 byte. It's just assumed the high byte is 0. So that's what, if you ever see any documentation with zero-page address, the high byte is just assumed to be 0. So if you only specify 1 byte, which is 2 hexadecimal digits right here, it's just assumed to be 0, 0, 0, 0, 0, or 4 zeros, and not 2. There's an advantage to using the 0 page in the Nintendo. It's faster. So a lot of the time you want to use like the variables you're going to access a lot in there, some of your working area, you want to use the 0 page. So you have a limited amount of space there to work in. And so you can notice that the literal for hexadecimal in the assembler is $00. So here's a 16-bit address that I mentioned before. This would be where you're typically, this range is where sprites start, but we'll get into that later. You can do hexadecimal literals. And the way to remember it is like, I want the number F. So it has an octothorpe first. So I want the number hashtag F. So that's just literally the number 15. It's not a memory address or anything. It's literally 15. So the assembler treats it as a number instead of as a memory address. And you can also do the same thing for binary literals, which are super useful because a lot of the Nintendo uses memory mapped ports to interact and set flags. So a lot of times you want to set like certain bits to 1 or 0, depending on what things you want to turn on in the Nintendo. So the binary literals are just useful just to see what flags you're setting, because in hexadecimal you're like, okay, what is that in binary? Gotta write it down. Or if you get like if you go to crazy mode like me and you just remember what things are in hexadecimal and binary, but that's not for everyone. So the Nintendo has a few registers, 4 of them actually. The first one is the accumulator register, which is the work register. This is like pretty much anytime you're doing arithmetic is going to be an A register. Adding, subtracting, doing crazy stuff, dividing, all the things. It's meant for doing the math. So pretty much if you want to do anything, you got to load it into A first, do your work, and then put it somewhere. There's the index register X, and there's 2 of them, X and Y. But these are basically meant for loop counters. So now you can have a double nested loop. They're pretty much meant for loop counters and memory offsets. So they don't have a reduced set of opcodes, so you can't really do all the things that you might want to do in math in X and Y. You'll have to do them in A. But you can move stuff in and out of X to A and vice versa and Y and that kind of thing. There's also the status register, which you can't set directly, but this keeps flags for like if you had an integer overflow in addition, or if you had an integer underflow in subtraction, or if the result of the last operation was 0, or a few other things. There's a whole list of documentation. We'll go through it later maybe if we have time. We have a lot of ground to cover. All right, cool. So variables are useful. So you could, if you decided, just remember what memory addresses your information stored in. It's like, if you felt like that. The assembler that I'm using has a really helpful thing for setting variables in memory, so you don't have to remember like, 0, 0, 1 or something, And it's like, okay, that's gravity or that's the ground or whatever. So that's nice. So in this assembler, we have the directive RS set, which stands for reserved space set, starting at memory address 0000, which is 0 page. And that's where I want to work on like my player X, player Y, all of these useful variables that I have. Reserved space, again, is I'm reserving 1 byte. I could reserve more if I want, and it'll reserve that chunk of memory for me. And the assembler will just stack this up for me and replace all of the instances of these words in my program with the memory address when it finally gets compiled. So you don't have to do that yourself. This actually, I was like, I can remember memory addresses, and I started that way. It quickly got to a point where I'm like, I just don't know what's going on anymore. So, like after I got to here, like things just spiraled out of control, and I could not remember what addresses were for what. So this is super helpful. Don't take it from me. Don't try to do that. That's a bad idea. So let's talk about opcodes and labels. So you might have kind of figured it out already, but labels are those big words that we have right here that initialize state, colon, and it can be any string that you want. And it's basically to help you organize areas in your program. It's basically like if you're thinking back to BASIC and you want to do like jump to a line or go to like line number, it's basically that. You just go to that label. You'll notice there's also opcodes. So there's LDA, STA, LDA, STA. You'll notice I'm doing a lot of load into A and then store from A. Like what I was talking about, that A register is your work register. And we'll get into the specifics here in a second, but that's kind of how it looks and it's operated. Opcodes themselves have to be indented. It's actually syntax error if it isn't in this assembler. You could write another assembler that has different rules, but in this assembler, it has to be indented. And I already talked about directives, which are just the dot something, and there's a few different directives. I apologize that this screen is not high contrast. A few of them in here are different banks, starting at a certain memory address, and this DW is stands for data word. I want to store a word into memory, starting at FFFA, and then continuing forward. And that's basically all that's happening. And there's another interesting one down here, this directive called include bin, which includes a binary file into the ROM. So it basically just copy pastes from your binary file into the ROM when it's finally compiled. So there's not a whole lot of magic here. It's just basically this is compiled into binary, and binary is glued on the back. It is the original concatenation. So let's talk about opcodes. So a lot of the opcodes are mnemonics. So LDA stands for load into A. And then I'm loading the literal value 15 in this case. And most of the registers have similar ones. You'll notice in these ones I don't have the number literal in front. I'm actually loading the value that's stored in that memory location into the X or the Y register in this case. I can do the same thing when I want to store values back after I'm done doing my work. So I might have done some calculations with the value in A register, and I want to stash it in this location in memory. So I'll go ahead and stash that value in the memory address 2000. And the same thing for the other ones. I was just giving different examples of addressing. One thing that you'll want to do, which I didn't have time to go over. Oh man, and this thing is just so slow. Anyway, in opcodes, they actually have different addressing modes too, so you can be tricky about how you access memory and indirect. Like there's one where you can indirect the value in memory as another pointer, so you can just double hop to read a value. So that might be tricky, and you might want to do that. But I don't have time to go over that, unfortunately. So here's the arithmetic. This is like the workhorse. So add with carry, ADC, add with carry, which takes the value in the A register and adds it to, in this case, literal value 1. So the formula that it does behind the scenes is A equals A plus 1, plus if the carry bit is set in the status register. So it indicates that like we had an overflow and we need to carry that one bit that we had in that register. Normally, if you want a fresh addition, you want to clear the carry and not have any like leftover carries from previous operations that you forgot about or don't care about. So typically, if you want a fresh addition, you're starting a new round of work, you want to clear the carry bit so that it doesn't mess with you when you're doing stuff. Subtract with carry, same deal. It has a pretty interesting formula. A equals A minus 8 minus 1 minus carry. So what you want to do if you're starting a new subtraction is you want to set the carry. So just to make things confusing, you do the opposite. So it's a pretty interesting formula. I'm not sure what inspired them to make that happen, but it does. You can also increment memory addresses, the value stored in memory addresses, which is super useful. I use it when I'm calculating velocity and gravity and distance and stuff like that. You can decrement values. You can increment values in the X register. Same thing for decrementing. And the Y register has those two opcodes as well. There's the arithmetic shift left operator, which will shift the A register left by 1 bit, which is a quick way to multiply by 2. And then you can shift right, which will divide by 2. And there's 2 other commands that I have, is rotate right and rotate left, which add stuff into the carry bit that you might want to use for, like, you're doing some funky math and you want to keep track of any bits that fall off when you're doing shifting. Otherwise, you lose those bits permanently when they shift off the end left or right. So, comparison. All right, this is how you might compare something to a value. Use this a lot when you're deciding whether or not you want to branch somewhere. So, like, if your counter is down to 0, you might want to do something. So, like, and there's a typo on my slide, but compared to 0, the status register will be set whether or not the last comparison, the last value was 0, and you might say, okay, now I'll jump or not. And there's a few other comparisons. The first one compares the A register against a value, and then you can compare X and Y the same way.
Does that set a status register?
Yep. Yeah, it sets a status register to know what the value is. And then in flow control, you'll be able to either branch if something is equal. So you can branch on equality. You can branch on non-equality after you compare. And that's branch that memory address, not like branch if this thing is equal to somewhere. So this is basically, I'm branching if equal to a piece of program that is located in FFF00 or FF00. And so that BEQ and BNE is branching based on a compare. So you do typically you'll do a compare for a value and then decide whether or not you want to go somewhere. And usually you'll use a label there and not a memory address. But I was just multiple examples of how you might call the opcode. But so you might say, you know, branch equal my function label, something like that. The JMP is jump, which is an unconditional jump. Means you'll just go there. It doesn't matter what you compared previously. You'll just go there. It's the same as a goto, really. I think a goto would compile to that. But the jump just goes there and executes that code next. So it might be useful to do something like that if you need to break your code into some smaller chunks, like to understand it. You might organize things like that. But then at the cost of you have to execute another instruction, which are precious on the Nintendo. So sometimes you make sacrifices on your code quality so that it runs faster. This next one's cool. JSR is jump subroutine, which actually does the proper function subroutine stuff. So you can jump to a subroutine and then return from subroutine, which will do the stack pointer. And I think you have 255 stack frames possible in the Nintendo. After that, you got a Stack Overflow and you're done. But so just no recursion. Or if you do, be careful. All right. Whew. All right, so that was a lot of distance to cover just to get to code. So I hope I have you all with me, and I hope it's entertaining still. So there's really only 4 things that you need to make a NES program. You need the INES header, which tells the Nintendo about your ROM. You need the callback vector, which is basically a callback to the code that it needs to run. And it's the Nintendo will look for that in a specific spot in memory, and if it's there, then it'll call your code. There's banking, which if you have a big ROM, you need to swap parts of your ROM in and out of memory in order to use it, because there's only so much you can work with. And then there's including binary files, which we already kind of touched on briefly. But you know, you might want to have sprite sheets or other bits of assembler that you want to include, or sound files, things like that. So here's the Nintendo memory map, and the 0 page fell off the bottom because the resolution here is not so great. But at the top is where you set your callback, NMI. So in the middle there is where your ROM sits, and then you have some cartridge WRAM. So if you have a cartridge that is bringing RAM to the table, you can expand the Nintendo's capability, and some of the more hefty carts would bring their own RAM that is packaged inside of a cartridge, like this, which is why cartridges are superior, because they can bring more hardware to the console. And then there's different memory map ports for controlling the PPU and APU, and then a whole bunch of other RAM for controlling internal Nintendo operation. All right, INES header. It's a 16-byte header in the beginning of your Nintendo game. The first 3 are the character codes NES, N-E-S, and then you set these flags, which the assembler sets the correct thing in there. I'm not sure what they actually compile down to, but it tells it okay, how big is my ROM? You can't read the comments in there, but the first one tells the Nintendo how big my ROM is, how much character data I'm going to load, if I'm using memory mapping or bank swapping. In this case, I'm not. And what kind of background mirroring I need to do for the scrolling, the wonderful scrolling that the Nintendo is known for. So that's the first thing you have to do. So first thing, start a new program, project, new Nintendo, drop that sucker in there. The next is you want to specify the code that you want to run. So you set up your callback vector. And those begin at the top of memory at FFFA, and it's always there. The first thing that you put in there is the NMI, the pointer to the NMI function, which stands for non-maskable interrupt, which is which happens in the VBlank, which is the period of time that the scan laser is going across your screen that is in between the bottom of the screen and the top. That is the VBlank period, and that's the time you have to run your game engine. There's this bit of period of time. The rest is spent drawing. So like the period of time when the Nintendo is drawing off the screen, that is the time you have to do your game logic and stuff. So there's the reset vector, which is what it sounds like. It's what happens when you push the reset button or the power button. So that's a function to do when that happens. And IRQs for audio, which we won't go into. All right, I wish this was better. So this is my main loop. So I have a label that just says NES callback. You'll notice that I'm starting at that position in memory, the 3 Fs and an A. And then I say, OK, store the label for my main loop right there, right in the first spot. So it'll go and call that. And then I have my reset label and then my data word. I'm not using IRQ, so I just set it to 0. So cool. All right, here's my main loop that I defined. So you notice I had the label main loop here, and I stashed it into that callback right in that memory location. Here's my main loop. So I try to keep my main loops pretty clean. You'll notice an opcode that I didn't tell you about, which is a special one which tells the Nintendo I'm done with this interrupt. And it's basically I'm done with this callback. So the Nintendo hardware will call this every time we hit the VBlank, and it'll do things like, OK, I need to prep my graphics. I have to do that every frame for it to work. I need to draw my game first and update. So normally in games, you update first and then you draw. But the problem is the Nintendo's, you don't have a lot of time, so you want to draw before you update. Because once you're out of time here, there's no opportunity. Once it starts drawing, there's no opportunity to change anything. It's not double buffered or anything. So you want to draw first. So I'm jumping to the draw subroutine here, JSR to draw. And then the same thing for update. So I try to keep the main loops tight, just so that you know what's happening. And then you just have a lot of times people just do like draw this, draw this, draw this, update this, update this, update this. I usually just stack everything in the draw function and the update. I don't know. It's personal preference. Cool. So that's a lot of wins to get there. Cool. So now you might want to, in your update subroutine, you might want to pull the controller for input. And through the magic of memory mapping, reading from these magic memory addresses in the Nintendo will give you the status of one of the buttons on the Nintendo. In fact, you have to read from this memory address in order 8 times, and it'll magically give you the status of each of the 8 buttons. So it'll be like, this is the A button, this is the B button, this is the select button. So the Nintendo, there's a side effect to reading a memory address in this case. So when you read this, it just increments to the next button. So same thing for controller 2, which is 4017. So you just read over and over and over again. I wrote a little helper to do that right here, which I call pull controller. It actually just pulls controller 1. And the output of this is it stashes into my memory location, controller 1. Man, high contrast, man. A vector that has a 1-byte vector that has a 1 or a 0, depending on whether or not the button is up or down for the 8 buttons. So conveniently, bytes are 8 bits wide, and we have 8 buttons on the Nintendo. So I can fit it in 1 byte. So if the most significant byte is 1, the A button is pressed. Then the B buttons start, select, up, down, left, right. So the way I do that is by first starting my X register at 0, because I'm going to start counting. This is a loop counter. So I go ahead and I do LDX, which load into X the literal number 0. Next, I go ahead and read that magical memory address for controller 1. And that magical memory address will give me the first button that I need to read. I think it's the A button at first. Yep. And then I go ahead and shift right, and then I rotate left, which shifts left, and the bits fall off into the carry. And when I do that, I rotate left into the controller variable, which is a nice feature of the rotate left. So I get that first bit stored into that variable in memory. And then I increment my X counter. This is the loop counter, remember. And I check if I'm done. So I compare my X counter, my X register to 8, which is how many buttons I have. And if I'm not equal to 8, we start over. So this is a branch not equal. So I'm not equal to 8, so I go back up here and we do it again. So we just go through that, and then once I'm done, this will not branch, and I'll fall through to this return from subroutine. Wow. It's a lot of work to read buttons. And that's something I realized as I was doing this, and I spent over a week doing this. So one thing that kind of, at first when you're first learning it, it's super slow because it's such a foreign concept, doing stuff like at one instruction at a time. The thing that kind of appears is this pattern of looping through memory is something that you use a lot. So this kind of like, this is the name of my function, and this is my loop helper label. And I just, this happens a lot. You'll see this in my code when I show it to you at the end. But that kind of thing happens all the time. So a lot of these patterns start to emerge as you start building things, and they're kind of part of your toolbox now, and you kind of use them. So this pattern is used a lot in assembler. I have this twice. Awesome. I was really tired when I was building this. All right, so after all of that, some basic programming. We did a basic loop, a little bit about how to start your code up and how to run it. You're going to want to draw something to the screen. So the PBU is a separate coprocessor from the processor, and it handles all the drawing of the sprites. The processor is already too busy running your code to do anything else. So that's why we have a separate coprocessor. If you've ever noticed in your laptop when you have the integrated graphics, that is all like CPU driven, and that's why your computer just really eats performance when, because now your computer's busy doing all the normal stuff and then also drawing your screen. So this is how they solve that problem. So the PPU, you can load in your sprites from ROM using a direct memory access method, and it's kind of a bit of magical incantation for the Nintendo, but once you got it, then you don't need to know how or why it works. But basically, all it knows how to do is how to draw things and put them on the screen somewhere. And that's what the PPU will do for you. So there's more magical memory ports. If you poke these, these poke the PPU to do certain things. You can look up what they do on NESDev, but the ones that we use mostly are this one, the 2000, which is the PPU control, which sets like the main settings for the PPU, like what colors am I using? Like, should it be very blue? Should I draw sprites even? That kind of thing. And then this one, which is PPU data, which is what you use to feed the PPU all your sprites. And these other ones do some scrolling, and there's some more data loading for various reasons. But we don't need to get into that. If you're really curious, you can look it up on NESDev. They have a wiki, which they document it in great detail, what each of those do. So let's talk about sprites quickly. Sprites in the Nintendo are 8 by 8 pixels wide, and that's it. If you want to build a character like this little robot guy, you have to compose them on multiple sprites. So each 8 by 8 pixel sprite is drawn here on the sprite sheet. I have some, I cut a little bit of it off, and I couldn't find any tools for this, so I wrote my own. So I open sourced this morning my sprite drawer tool that if you guys want to make sprites on the Nintendo, you can use. But the other thing is you have a maximum of 4 colors per sprite. So that's it. You can't use any more. Even though you have 48 colors on the Nintendo, each sprite is limited to 4 colors. In fact, it's only 3 because one of them has to be the background. So you really only have 3 colors to work with. So that's fun. So really just like limiting your capabilities. But the cool thing is some games like flip palettes on the fly, so you can kind of trick it into doing cool things in more colors. So you can be kind of creative there. So there's 2 types of sprites. There's character sprites and background sprites. Character sprites are drawn in the foreground. Think Mario, Goombas, Koopas, that kind of stuff. And I have an example from my quote-unquote game that I was doing. You can see the little robot moving around on the screen. That is a character sprite. Everything else on the screen is a background sprite. So let's talk about background sprites. or maybe not. I guess we're going to load them first. Man, I just need to practice more. So this is the code to actually load sprites into the PPU with a direct memory access method. It's pretty simple. This loads the sprites that I have in my ROM, which I have a label for. That's that player sprite. So starting at 0, I have that player. See, this pattern is very familiar. I have the sprite in my ROM. I have a label for it called player sprite, and I go through and stash my player sprites at address 200, which is the typical place to put sprites and sprite data in the Nintendo. And then I go through until I hit, this documentation's wrong, but until I hit 1C, which I think is 28 in decimal. It's 116 and a 12, right? 28. Yeah, I can do math. Yeah, so so then we're done. And then once I do that, all I have to do is do this direct memory access thing and tell the PPU where to start reading sprites from. So that's this bit right here. So so this is a PPU port 2000. I set the low byte of where I need it to do direct memory access, which is 0. Notice it's 00 right here. And then I set the high byte inside of a PPU register, 14014, or 4014, and then it'll just read it all 64K. And I don't have to tell how long. It'll just read all 64 bytes, excuse me, not K, 64 bytes of character data from starting at that location. And then they're available to the PPU, and it can draw them. Cool. We already talked about this. I don't know who drew these slides. But one cool thing to note about, or one bizarre thing to note about how sprites work in the Nintendo is you would expect the binary layout to be like the first 2 bits, encode pixels 1 through, pick either color 1, 2, 3, or 4, right? It's either background or color 1 or color 2 or color 3, right? That would make sense, the first 2 bits, because you have enough information for that, right? That is not how it works, because that makes sense. You use 2 bytes, 8 bits are 8 bytes away from each other, so byte n and byte n plus 8 encode the color for any 1 pixel. So, for instance, in this sprite with the circle on the red that I have highlighted with this palette, with black being the background, this little light teal being color 1, color 2, color 3, I have an illustration of how this works. So I have byte 0 for this row of pixels, and then byte 0 plus 8 for this row of pixels looks like this, and then that means this is the color. So basically it's, you take channel 1, it has a weight of 1, and you have channel 2, which has a weight of 2, according to the documentation, and you add them together, and that is the color for that pixel in that row. So this is this row. This is pixel 1, pixel 2, pixel 3, pixel 4, and then you can see that I have color 2 set for those 3 pixels in that row. So you can kind of see that happening right here. So there's 1, 2, 3, and that's that blue pixel. Mind blown. It is really difficult to draw stuff when that is how it's laid out, because you're like, I want to think in color. I don't want to think in like, okay, I got to add 2 bytes together. Kind of. It's not really adding. I have to add 2 bytes together to get a color. So, and it gets even crazier on this next row, where we have the channel 1 is all set to 1s, and then set to 2, and then we get this color, because this first channel has a weight of 1. So if there's a 1 times 1 in that digit, then that's the eventual color, plus the 1 times 2 in that digit equals that color. So unfortunately, I don't have any color 3 examples in this one, but you can see how crazy it is. And why I needed to write my own tool, because I was like, oh, maybe I can just do this in a hex editor. No, I tried. I got like 1 sprite, and I'm like, this is the worst. I have to write something. So that's colors. So once you have a sprite loaded into memory and you have it all drawn out, the way you draw sprites is actually pretty easy. Remember that memory address starting at 200? Well, you can position them using these parts of memory. So starting at 200, the first byte is your Y position. So if you set byte 200 to 00, that is the top of the screen for that sprite. EF is the bottom, and there's like some space at the bottom so you can fall off the screen. Actually, I think there's a whole v-blank section there. The tile index, which is the actual index of that sprite in the PPU. So the index is basically just the order you added it. So the first sprite that you added to the PPU is sprite 0, and so on and so forth, up to 64. Attribute is basically, okay, what do I want to flip it? Horizontally or vertically? Do I want it to be in front of the background, which is usually yes. Unless you're playing Super Mario World 3 and you find the secret whistle, then the answer is no, and you want to set that to a 1. And the last 2 bits are the color palette. So you have a possible 4 palettes for your sprites, which you can define later in the, I think I defined later in here. But basically you have 4 palettes. Each palette can have 4 colors. Yay. So that means you can only have really 16 colors at a time being drawn. But you can swap them in and out so you can do cool things that way. And you can exercise all 48 colors if you want. And then the horizontal, which you would expect to be the first byte in the series of 4 bytes that defines the position of a sprite, is at the end. Byte number 4, the X position, is 0 is the left and F5 is the right, which I think is cute because I work on that daily. Cool. Anyway, so here's an example of me actually doing it for my player sprite. So that little robot that you saw is composed of 7 sprites. So I'm positioning it in about the middle of the screen, byte 80. I'm using sprite number 0, which is the first sprite I loaded in. I don't have any fancy pants attributes for it. Probably could have saved a couple sprites if I flipped them. And then the horizontal position. So I do that for 7 sprites. Awesome. Then we talk about background sprites. Whew. We're just going to bust through this real quick because I'm pretty sure that you guys want to see a demo or something. So backgrounds are defined by the name table, which is quite possibly the most confusing thing I've ever read in the Nintendo. So I'm going to try. We'll see how far we get. I still don't fully grasp it because there's a lot of things you can do, and it's mostly because they wanted to enable that cool scrolling behavior that you see, like that very smooth scrolling of screens, and that's why I think it's so complicated. But there are 4 name tables in the Nintendo, but really only 2 because the other 2 are actually just mirrors of the other 2. Either they're horizontal mirrors or vertical mirrors, and that was specified up in your iNES header at the very beginning of this talk, which you may or may not remember. The background is also 32 by 30 tiles wide, which means you have 960 bytes, which presents a problem because remember, it's an 8-bit machine, and those loop registers only go up to 255. So I can't count to 960 easily. So I have to do some fancy pants, like I have to use 2 bytes to count to 960. So maybe we'll show that later, but it's pretty nuts. To count to 960 is actually hard because those registers only go up to 255 because they're 8 bits wide. So making it further more complicated. All right, so once you have that, that tile selected, so we have 960 bytes. Each byte is just the tile index of the background sprite. So we have 960 bytes to do each background sprite, which is 8 pixels wide. That's why it's 32 by 30. So each background sprite just will go in its proper order. The attribute table is what determines what color they are. And it's not like this is even more nonsensical than the sprite byte layout. But the attribute table, you have 64 bytes to describe all of the colors for everything in the previous name table. So after that 960, there is a 64 byte array that is tacked on the end. And this defines the colors for the name table. And it is defined into a series of 32 by 32 pixel grids. So like 32 by 32 pixel grids here chopped up. So you'll see that we have 16 by 16, so that's 32 pixels by 32 pixels. So we have 1, 2, 3, 4 sprites by 4 sprites tall. So if you're already confused, welcome to the club because it's very confusing. It's really hard to keep in your head. So each attribute byte is encoded like this. So starting at the top left, you give the palette index, which is like, so this, remember there's 4 palettes that you can use. So, and each can only have 4 colors in it. One of them has to be the background. So the first sprite, that 2x2 chunk in that attribute byte has to be a palette index. So it's palette index 3, and then that 3 goes here, which is the least significant portion of the attribute byte. So it's not like left to right reading. You have to like stack it up from right to left. So the 0th position goes here. The first position goes here. The 3rd position goes here, and the 4th position goes here. Oh my God. So yeah, mind blown. So really what I've done is I just said, screw that, I'm just gonna use zeros. I'm just gonna have one palette for the background. So my attribute bytes are all just 0. So, because I couldn't be bothered to figure that out. We have a demo, yay! Oh, I'm so sorry that it took this long to get here. So let's go over to the TV. I turned off the TV. All right, now you get to watch me load a cartridge into the Nintendo. This takes a lot of skill, especially now that I replaced the connector, because now it really grabs the cartridges instead of like a old school one where it's very easy to put them in there. This one really just holds on to the cartridges with a vigor. Aha. Hey, there we go. Sweet. Can you guys all see that? I'm not going to stand in front of the screen for you. I'll do it from this one. Start here. All right. Yay! He can jump and go across the screen. So one cool thing about like that, remember that sprite X position, is it's only a byte, right? So when you roll over, you just start back at the beginning. So it has forest worlds implemented because it's only 8 bits wide. So you can just do this for all day long. It's really hard to do, believe it or not. I had to go, like I had grand visions for this, and it definitely did not happen. So, but this is where we got. So this guy's built with 7 sprites. The background is built with 1 palette, and then I drew the backgrounds and stuff on here. So I want to go through the code with you real quick, because I think that'll be interesting. Okay, let's see. Code. Oh man, is there a way to get this into like a high contrast view mode?
Yeah, file, preferences.
I didn't even think about that. Let's do high contrast. Let's do, how about light? Yeah. High contrast is pretty nuts. All right, so this is the assembler for that game that you saw. And unfortunately, I don't have the little helper to colorize it for you. Let's actually zoom in maybe. Can I do Control Plus in here? I can. So let's talk about it. So I have a lot of comments in here. I'm going to open source this so you can download it and just copy paste my stuff. So here's that INES header that I talked about. Here are all those variables that I was talking about where I was setting them. They all start at 0. Notice that there's quite a few. There's the X, Y. There's the velocity of an X, velocity in Y, that controller vector. I have gravity, which is 1 pixel every 3 frames. So that's why the jump is a little wonky. I have to do a different mechanism for doing that. I also have where the ground is so that I can stop falling. I also have a byte that tells me if I'm in the air right now, because I don't want to accept controller input if I'm in the air, right? Because otherwise I could just jump up off the screen. Kind of like Super Mario Smash, or like that game. Okay, so let's look at some interesting stuff. Here's my reset. It's a bunch of clearing memory. I'm loading in palettes. You've all seen that loading stuff. Let's go to interesting stuff. Oh, here's that crazy stuff to count past to 960. This is nuts. But basically, I keep track of the low and high bytes of the background that I'm at. And 960 is the literal value 3C0. So I have the low bytes and the high bytes, and I increment each one and carry them if I need to. And that's how you do through 960. You could do it with the X and the Y register and do a double nested for loop, but I didn't want to do that because I was stubborn. Cool. Let's see, I think I have an initialized state. So here are those variables that I had, but here's me initializing them. And you notice this pattern is very common. You do load A, store A, load A, store A, load A, store A. So for each of those variables, I'm setting, okay, my initial player X position is going to be about the middle of the screen. So I'm going to load, 8 times 16 into A, store that into the X position in that variable that I saved 1 byte for. And to do that same thing for the Y, I'm going to put the player in kind of in the 0 position. I'm going to say that the ground is at YC8, which is, if you see my screen, that's where his feet are touching. That's at byte C8.
Yep,
10 minutes, awesome. That'll be enough time to finish on time. And then I initialize my controller to 0. And then since A is already stashed with the 0 value, I don't need to reload it to store the same value. I probably could have optimized this and put it down here. So I just store 0 into all of these right off the bat. And then I have my gravity that I set right here. So this is just a hack to make sure that the Nintendo doesn't exit early, because this is the main loop that actually gets executed by the Nintendo. So you can see that same logic that we talked about, where the main loop will do the draw first, jump subroutine draw, and jump subroutine update, and then return from that interrupt. So let's take a look at what that draw looks like. A little more complicated than you might have thought. So I have a subroutine to draw the player, which all that really does is it just sets that X and Y position on the sprites in memory for me for that player. And that's really what drawing is basically setting the positions on the screen. Then the PPU gets messed up every frame, so you need to clean it up. So this is some magic incantation that you need to fix it. But basically, I'm telling it, yes, I want to draw sprites. Yes, the sprites come from this location. And yes, this is the background I want to use. So basically, that's what's happening. We're not going to go through that. It's too complicated. Let's look at the draw player loop. So this does have an X and a Y register counter in it. So when I'm drawing the player, what I'm doing is looping through all of the sprites and then setting their offset a certain particular value. So you'll notice I am doing this really interesting comma X thing. And this is a type of addressing mode that says, take this number, add the value of X to it, and then load it. So it's kind of a neat way, to index through memory. And that's why these X and Ys are used for indexing. So this is basically saying, okay, so this is the X position. Right? Remember that I have 4 bytes starting at 200 that define each sprite. So the first 4 bytes define the first sprite, and so on and so forth. So this is the first sprite, X0, first sprite. Load that X position. Go ahead and clear my carry bit, because I want to start a new clean add. I'm going to go load the offset of the sprite that I need, which is how I'm positioning the tiles around a certain position, and that's what I'm using the Y for. So I have a whole bunch of offsets, which it probably behoove you to see. So we saw the 7 sprites that define my player here, and then here are my offsets that actually determine the position from the origin of my player. So I'm doing some tricky things, but basically I'm moving that first sprite, which is the top corner of his head. That's -8, -16 from his feet. And then that next sprite that I draw is the middle of his head, which is 0 from the origin, and 16 up, which is to go up, he's negative. And so on and so forth for all 7 sprites. And I'm being tricky and using 2's complement to subtract by adding, because I know I only have 8 bits. I can subtract by doing this really neat trick. Otherwise, you could subtract too. It's a perfectly valid way to do it. It probably would have been less confusing if I just had like 0, 8 in there, and then I subtracted in my code, but I wanted to be tricky, I guess. I'm sorry. So people look at that, it's like, I don't know how he's subtracting right now, but it's really crazy. So I load that value. So that offset for that first tile, in this case, which is -8 in the x and -16 up, I add that to the current player x value. And that's my origin, right? So that's my x value. Okay, I'm done with that y value, so I'm going to go ahead and increment it. So the next time I go through the loop, I'll have my updated y. Now I'm going to go ahead and store that. So I've calculated his new x position for that sprite, for that chunk of his head. And I go ahead and store that using that same method with this addressing mode, where I could say 203 plus x. And then now we're going to go work on the y position. So that was all just to figure out the x part of that first corner of his head. So the y position is stored, remember, in that first byte on the, starting at 200. So I go ahead and load that in. I go clear the carry, do the same thing, find the offset there, increment the y register in the offset, go ahead and store that back into the sprite. And since I'm jumping by 4 bytes each time in this loop, I just increment x 4 times, which is actually pretty common. There's not like an inc4 or anything like that. It's actually pretty common in assembler just to do this 4 times, because it's actually, I think, more efficient than loading up the number 4, adding it to the register A, and then transferring it into register X. Yeah, I think it's actually more efficient to do this, which is bizarre, because it looks bad. And then because I have 7 sprites, all 4 bytes wide, I check if I'm done, which is the number 28, which is 4 times 7, which is 1C. And then I loop, otherwise I bounce back. That's a lot of stuff. The sheer exhaustion on my face when my roommate would come in is like, how's it going? I'm like, it's not good. It's not good. So that's the drawing. That's basically what you do, is every frame you're just repositioning the sprites that you've already loaded into memory. To do the updating, go ahead and latch the controller, which sets the controller. The state that the controller is in right now is the base state, is what latch the controller means. So that's why when you ever start a console with a button pressed, you get all that weird behavior. That's what's happening. And then I do that pull controller method that you saw earlier. I go ahead and read the different buttons, and I update my loop, and I update my player position. So player position is very complicated. I understood it last night for about 5 minutes. I don't know if I could explain it again. So we're not going to try. But let's look over controllers. So there's the pull controller code that you saw before, and it stashes all of the button states into a 1 byte wide memory location named controller1. And what I do is I go ahead and use this really nice binary literal to test which button I'm pressing. So I load up my controller. This bit right here is the right button. So I'm going to AND it with that bit. And if the result is a 0, which is branch equal, then I'm done. Or wait, no, I have it backwards. If it's not pressed, 0. Okay, yeah, no, that does. Okay, so if it's not pressed and it's 0, then we're done. Otherwise, I go ahead and this is a carryover from stuff, so this actually doesn't matter. This is an extraneous load A, so we don't need that. I go ahead and clear. I load the X position of the player. I don't need to do that, I don't think. Oh, no, I do. I load the X position of the player. I go ahead and add 2 to it to go left and right. So I add 2 if you press the right button. And I store that back in the player X. So same for the left. It's just a different bit there, so this is some copy-paste stuff. The left, I'm, again, doing 2's complement. So I'm doing a tricky -2, which is FE. Which is 7 ones and a 0. So that's -2. So again, very tricky. And then same thing with the A button, where I'm testing the same thing right there. And I do a little bit a different thing where when I press the up button, I also stash that you're in the air by setting a 1-bit flag that you're in the air, because I don't want to accept controller bits anymore. So like right here, so if I'm in the air, I'm going to see if I am, and if I am, then I'm not going to accept controller input. So, because that way you can't jump multiple times while you're in the air. Whew, it's a lot of stuff. And I think that's my time. I think it's my time. I'm getting the eyeball of time. All right, so that was a lot to run through. I was talking nonstop. I hope you found that useful. The presentation's up on my GitHub, public, so you guys can use this as a reference, as a springboard. I'm gonna open source all the code and make all that the art assets copyleft. If you want to do sprite editing, you can go and visit my sprite editor on my website, and you can draw cool things, you know, like, and then save them as NES files, and you get the actual binary files that you need. It's all JavaScript, so of course it would be. I have a whole bunch of resources. There's the NES reference, the PPU reference. There's the link to the assembler that I use. There's a link to the Power Pack purchase. So you can buy the Power Pack if you want from this guy's janky website. And I actually put my credit card in here, so just say it appears that I have not had my identity stolen. So take that for what it's worth. And I tried to write my own hex editor doing this, and it turns out that's a bad idea. Use HEXEDIT instead. It's just a really great hex editor. That's all like looks really professional, very profesh. And it's so like you can edit bytes all day long. It's super great. And then the last thing I'll recommend is I went through this forum post on NESDev or Nintendo Age, excuse me. It's a super janky forum, but this guy actually had really great stuff, and I stole a lot of his code for this presentation. So don't think I'm that smart. Okay, it's not working, so we'll just go ahead. And thank you for helping me build more Terminators. As it was a lot of fun. I hope you guys had fun. I have a book to give away. So.
Yeah, we can start counting off. Eric, you want to go?
1, 2, 3, 4, 5, 6, 7, 8,
9, 10, 11, 12, 13, 14, 15,
16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38.
Is that it?
Magic number is 17.
17. Yeah. You are the lucky recipient of programming 6502. Also, the other variants, if you want to do SNES programming. All right. Thanks, guys. As always, it took me 2 weeks.
2 weeks.
This took me 2 weeks, but it's mostly because I didn't understand any of it when I
So the
started.
expectation of building the next Super Mario is pretty high.
You really appreciate how much work went into Super Mario when you try to do this.
Now, could you build
I don't know, but it must be a lot.
could you build some